So lecture 3.2. Exact analytical transient response characteristics of first and second order systems. So in the previous lecture, in 3.1, we talked about the 4 different transient response performance criteria that we are going to use: the rise time, the peak time, the settling time, and the percent overshoot. So those are the 4. And for each order of system, we could try to come up with a relationship between the parameters that we typically use to define such a system and those performance criteria. It's a very useful thing to do, but that really breaks down after first and second order systems. Third order systems you could think of as having multiple, maybe like a time constant and then a natural frequency and a damping ratio. A fourth order system, you might have 2 damping ratios and 2 natural frequencies. You could have different sorts of things when you get to the higher order systems. But analytically, it becomes more and more difficult to relate the parameters to these higher order systems, and especially when they start to involve zeros as well as poles. How do we relate the performance criteria to those systems? And especially when it has zeros, when there's zeros come in, it's becomes almost like all bets are off in terms of your drawing a direct comparison. So what we're going to do is just develop these exact analytical relationships between first and second order systems without zeros and the performance criteria, so rise time, settling time, etc. And then we're gonna try to use those to approximate higher order systems or systems that are first and second order but have zeros in them as well. We'll talk about when it's valid and when it's not valid to do that. But we'll still often, even when it's not super valid, we'll still often just use it anyways, knowing that it's not super valid and we might get a result that's not what we quite thought, as a starting point for iteration using simulation. So that's our even though it isn't always a great approximation, we'll still use the second order approximation. So let's look at first order systems first without zeros. I've got this typo, which is really great. A first order system without zeros has a transient response characterized by a time constant that appears in the total response as being the divisor of time and the exponent of the exponential term. The transient exponential decays such that in 3 time constants, 3 tau, only 5% of the term remains. In 5 time constant, less than 1% remains of the transient term. Okay? There is neither peak nor overshoot for this type of response. So this is just a decay, right? I mean, we've got a really good idea of what this looks like. It just looks like that, right? It's just an exponential decay to some new value. We're thinking about a step input, of course. However, the rise time for these systems is found by solving the time domain differential equation 3.2, where we take the input u to be the unit step function. We could use any step function, right? But we might as well use the unit step function. And is easily shown that the solution to this equation is given here, where k is the scaling factor on the step function. Okay, from which we discover that the steady state value is just whatever it is that scales the input. The rise time is, by definition, the duration of the time interval t1 to t2, such that y of t1 is 10% of the steady state and y of t2 is 90% of the steady state value. So we just plug in and get some equations here. So if we plug in 3.5a, so that's 10% value, we have the steady state value, so we can plug that in, 0.1 times k, and we plug in t1, We solve for what T1 should be, and T1 is about 10% of the time constant, of one time constant. Okay. Solving for an analogous, or in an analogous fashion for T2, we get that that's about 2.3 times the time constant. The interval then is the difference, so we subtract T1 from T2, and we get about 2.2 time constants. So 2.2-ish time constants is the rise time for a first order system with no zeros. Okay? And we can write that. There's actually an analytical expression too. So T rise is equal to exactly negative tau times the natural log of 9, which is equal approximately to 2.2 time constants. Great. So that's nice because when we have a system that's described by a first order differential equation, we can just know this is what the rise time must be.
And is that for all first order systems?
All first order systems without a zero. If there's a zero involved, then this is not true anymore. And we'll talk about how we could still sometimes maybe use this approximation and feel good about it. But at the end of the day, what we typically do, if we have anything besides a first order system without a zero, is we're going to simulate the result to make sure to check that we actually meet our performance criteria. So finally, the settling time can be derived in a fashion similar to the rise time. And the settling time, it turns out, is I think it's 3.9 time constants. Let me check my notes, but I'm pretty sure it's 3.9. Yep, 3.9. Good. So that's for first order systems. The only two performance criteria that are actually defined for a first order system are rise time and settling time. And they're just functions of the time constant. So the time constant is related to them in this way. I mean, it's pretty predictable. It's not too earth-shattering there. Okay, second order systems without zeros. So once again, remember this is without zeros, but we're going to look at second order systems as well. So second order system transient responses are characterized by a natural frequency omega n and damping ratio zeta. It is helpful to recall the complex plane graphical representation of the pole zero plot for a second order system without zeros, as shown in figure 3.2. So that's actually up here. So you've got one pole, you've got another pole, and they're either going to come up as complex conjugate pairs, or they might show up as a real pair as well. That can also happen. So remember that the damping ratio being greater than 1 is all this stuff out here, right? So if they're real, so zeta being greater than 1 means that the poles are on the real axis. If it's critically damped, we have a double pole at this branch here, which is zeta equals 1. And then if you decrease the damping, so this would be zeta between 0 and 1 along this arc, all the way up to zeta equals 0 here, no damping. And if zeta is negative, then we have an unstable system, right? So that's the damping ratio relationship to where the pole locations are. Remember that the radial distance here is the natural frequency. The natural frequency is related to the damped natural frequency, which is just the natural frequency times the square root of 1 minus zeta squared. The other way that geometrically we can relate this is that this angle here of the poles is the arc cosine, a cosine of zeta, and the real part here is negative zeta omega n. So it's good to keep this in mind. We're going to start using this more and more, this pole zero plot representation, and so keeping this in mind while we're doing this part is going to be good for us to do. So, good. Following a procedure very similar to that for first-order systems, the following relationships can be derived. The rise time does not have an analytical solution in terms of the natural frequency and damping ratio. However, Figure 3.3 shows numerical solutions for TR scaled by the natural frequency for underdamped systems. So zeta between 0 and 1, we have this relationship between zeta and the rise time times the natural frequency. So if you've got the natural frequency, you've got the damping ratio, you can find the rise time from this. If you've got the rise time and the damping ratio, you can find the natural frequency from this. So you can, if you've got two of them, you can find the third. Now, there's no closed form. It's because it's the relationship is nonlinear, and there's no closed form solution for the rise time in terms of zeta and omega n. That's why we have this plot. You can use the plot. You can read off the graph, and there's a similar graph in the textbook. I think this one's a little bit. There's a little bit more finer of a grid on this plot, so I think you can find values a little bit easier on this plot. But just there's also a numerical. I could probably give you guys a script too if you guys wanted to find the rise time given zeta and omega n. But this is probably as good as anything for that. Keep in mind that we'll usually be using this as an approximation anyways, so exactitude is not always important. Great. The peak time, TP, has the following simple expression. So the peak time is related to the damped natural frequency with this simple relationship. It's a pretty cool relationship, and so it's good to keep that in mind. So the peak time is much simpler than the rise time for second-order systems to describe. The percent overshoot is related directly to the damping ratio. So it doesn't depend at all on the natural frequency. It's just the damping ratio. So you could think of the damping ratio determining what the percent overshoot is, or the percent overshoot determining what the damping ratio is. And I've solved it out in both ways. So I think this is the one the textbook has, and I've also solved for zeta and gave that to you as well. I don't think the textbook has that one. I could be wrong. So this is our zeta percent overshoot relationship. Finally, the settling time is just 4 divided by zeta omega n, which is a nice, easy relationship as well, and allows us to set performance criteria accordingly. So we can translate them between the transient response performance and the second order characteristic parameters like zeta and omega n. Okay. Any questions on that? All right.